Now let's recall we mentioned before the building blocks of all the functions we need in this course in calculus. I meant the building blocks. Okay. 6 classes of functions, if you can recall handout number 1. Okay. The first class, constant functions. In the first class we have constant functions. Okay. The second class, power functions. Power functions are the functions in the form of x to the power of n. Constant function is a function like the function is 5, is 6. Okay, it's a number. The next class, if it was real face-to-face class, I would ask people the next class. I believe now you can remember the details. Okay, so leave some blanks here. The next class is exponential functions. Exponential functions, the general form is a to the power of x, right? A is called the base. A is called the base. Exponential functions. Okay. The fourth class, log functions. Mute your microphone, please. Log functions. Okay. Log to the base a of x. We say the function log to the base a of x. Okay. Again, for the people who joined the class late, I want you to download handout number 6. Okay. So today I'm going to mute your microphone, please. It's broke. Okay, thank you. Cool. And then the fifth class, all the trig functions, right? So leave some blanks in between. So later on, I'm going to give you some basic formulas. Okay. The fifth class, we have all the trig functions. We require 6 trig functions. The first one, I believe, is sine of x, right? The next one is cos of x, cosine of x, and then tan of x, or tangent of x. Okay, and then cotan of x. We require 6 trig functions. The next one should be secant of x. Okay, and then the sixth one should be cosecant of x. We reviewed many properties of all these functions. Actually, so today I want you to know. So there are 3 inverse trig functions I want to require. Okay. The next class, the inverse trig functions. The first one is inverse sine. I know I did not review inverse trig functions, but at this point you just need to know the 3 inverse trig functions are also in the building blocks. So today I will symbolically learn how to differentiate the functions. So later on I'm going to tell you why. Okay. At the right point I'm going to tell you why all the basic differentiation formulas are true. Okay. But the sixth class, the first one is inverse sine of x. We use a notation like this to denote inverse sine of x. Or some people also call it arcsine of x. Okay. It's the notation is the same thing as arcsine of x. Okay. Yeah, I said arcsine of x. Here, inverse sine is a function notation. I will make more comments later. Okay. The next one is inverse cos of x, or arc cos of x. The same thing. And then we require only 3 inverse trig functions. I know it's possible to talk about the inverse secant and the inverse cosecant. Okay. The next one is inverse tan of x. Or some people say arctan of x. So the same thing. At the right point, we're going to do the inverse trig functions. We're going to study inverse trig functions in more detail. But now I want to include the 3 inverse trig functions on this list. Okay. Again, so today I'm going to release the basic formulas for differentiating all the building blocks. A proper term is the derivatives of all the basic elementary functions. On the screen you have all the basic elementary functions, right? Now I'm going to release the formulas for differentiating or taking the derivatives of all these functions. Now the title of the slide is something like, so can I just call the derivatives of basic elementary functions? I'm going to release all the basic formulas. Okay. At this point, you just memorize all the basic formulas. Again, your midterm and the final could be closed book. There will be no formula sheet. You need to memorize all the basic formulas. The first class, to differentiate the constant. Very shortly, I'm going to tell you why. Okay. You remember the derivative of a constant is equal to 0. I'm going to release all the basic formulas first. Okay. The derivative of any constant is equal to 0. Very shortly, I'm going to tell you why. Okay. Last class, I think we mentioned the power rule. The power rule is for handling the derivative of any power function in the form of x to the power of n. The power rule again is for handling the derivatives of all the power functions. Okay. Anybody can recall the formula I told you last time? I think last time we were trying to use the derivative of x to the power of 3 to generalize the formula. Okay. Yeah, probably you can look at your notes. I told you the formula last time, so this time you just memorize. Okay. Just memorize the formula. The derivative of x to the power of n is n times x to the power of n minus 1. So thank you. I think we mentioned the formula last time. We mentioned why the formula is true for x squared, for x cubed. Okay. Actually, we mentioned some other formulas. There are two particular cases I want you to memorize. The two particular cases, very shortly, I'm going to tell you why. But in the future, you are going to see the derivatives of the following power functions over and over again. I really do want you to memorize the two special cases. Actually, we mentioned the two formulas last time. We used the definition of the derivative. I showed you why the formula is true. Actually, you want to recall I told you to memorize the derivative of square root of x? That's actually a particular case of the power rule. Okay. The derivative of square root of x is a particular case of the power rule. It's because we can treat square root of x as a power function. So very shortly I'm going to make more comments. But now I want you to memorize that formula. Okay. The derivative of square root of x is 1 over 2 square root of x. You check your notes. We did that last time using the definition of the derivatives. Right? That's one particular case. The other particular case I want you to memorize is how to differentiate or how to take the derivative. I'm trying to say the same thing in different ways using different terms. Actually, the same thing. How to take the derivative of 1 over x. The derivative of 1 over x, we also did that last time using the definition. Right? The derivative of 1 over x is equal to negative 1 over x squared. You check your notes. Okay. Again, I'm looking for proper notations, so do not forget to use the prime notations. Okay. The third class of the building blocks are exponential functions. Exponential functions. Okay. Now let's recall there's a restriction on the base. The base is always positive, and the base cannot be 1. Okay. We do not have to mention that in here. But I'm going to tell you the formula for differentiating any exponential function a to the power of x. So just remember the derivative. Okay. the derivative of a to the power of x is a to the power of x times natural log of a. Later on, we're going to practice many questions designed for practicing how to use the basic formulas. Okay. But at this point, you just remember the basic formula. Okay. There's a particular case for exponential functions. When the base is e, we have a function e to the power of x. Okay. I told you this is probably the most important exponential function in calculus. Okay, the derivative of e to the power of x is equal to, now look at the formula. Now look at the general formula. Okay, is equal to e to the power of x and then times natural log of e. So anybody can tell me what's the value of natural log of e? That's a famous value we reviewed before. What's the natural log of e? Natural log is a log with the base of e. To get the natural log of e, you think e to what power is equal to e, right? So this value is 1. So we do not have to write the factor of 1, right? You just remember e to the power of x is, the derivative of e to the power of x is itself. So this is the only function having that property. Of course, there could be some constant factors involved, but this is the only function having that property. The derivative of e to the power of x is the same as the function itself. Again, I'm releasing all the basic formulas. It's kind of your formula sheet. So in the future, you are going to differentiate the functions over and over again. After this, we are going to learn some differentiation techniques so that eventually you are going to be able to differentiate any function as long as the function can be written using one formula. By that I mean we are going to be able to differentiate any elementary function. You are going to see probably in less than a week you are going to be able to differentiate all functions. It's kind of all functions. Okay, now to differentiate the log function, the general log to the base a of x. You remember the derivative, the general form. Okay, the derivative of log to the base a of x is 1 over x and then times natural log of a in here. Okay. A particular case of this is how to differentiate natural log of x. The derivative of natural log of x. Again, natural log is a log with the base of e. Okay. Natural log is a log with the base of e. So to differentiate natural log of x, you should have 1 over x according to the general formula above. Okay. 1 over x times natural log of the base. The base in this particular case is e. We just mentioned the natural log of e is equal to 1, right? So the derivative of natural log of x is just 1 over x because natural log of e is 1. Okay. Again, for the second class, how to differentiate power functions. The third class, how to differentiate exponential functions. The fourth class, how to differentiate log functions. I give you the formulas for the basic form first, okay, and then there are some special cases. So try to memorize the formulas, okay. And then how to differentiate the trig functions. The basic formulas. I'm not going to make too many comments. You just copy the formulas. Again, at the right time, I'm going to tell you why all these formulas are true. Okay. The derivative of sine of x is cos of x. The derivative of cos of x is equal to negative sine of x. The derivative of tan of x is secant of x, the whole thing squared. I will make more comments on these notations later. Okay, so can I make some comments right now? I think I can make the comments right now. I just mentioned the derivative of tan of x is equal to secant squared of x. You write the little squared in here. You write the little squared in here. So this thing, it means secant of x, you take the whole thing squared. This is not the same thing as secant of x squared. So do you see the difference? The last notation, it means you take x squared first and then you take secant. So can you see the mouse cursor? So this notation, it means you take secant of x first and then you take the whole thing squared. Again, if you write the little square in here, it means you take secant of x the whole thing squared. In many cases, I just say that secant of x the whole thing squared. If you hear I say secant of x the whole thing squared, it means secant squared of x. It's not the same thing as that. Yeah, probably you were told about that before, but I just want to remind you. Alright. And then the derivative of cotan of x is equal to negative cosecant of x the whole thing squared. So that's why I say the whole thing squared. And then the derivative of tan of x is equal to secant of x then times tan of x. And the derivative of cosecant of x is equal to negative cosecant of x then times I'm trying to read their question. What if you did the cosine? Okay, so I'm not 100% sure if I fully understand your question or not. So, but secant of x the whole thing squared, it just means secant of x the whole thing squared. I know there's a common mistake in here. Secant squared. Okay. This notation itself does not make any sense. Secant is a function notation. Only when you follow secant, so by some x or by some number, it will make sense. I'm trying to say, so do not treat secant of x as secant times x. It's not the same thing. It means secant of x. Secant is a function notation. It's comparable to f. It's comparable to f of x. I hope I answered your question properly. I know there could be a... Yeah, I think I got it. And then that's where we left. Cosecant of x, the derivative of cosecant of x is negative cosecant of x then times cotan of x. Three more formulas. So don't be too scared. So there aren't too many formulas I want you to memorize. Yeah, that's why you remember in the first week I told you to kind of remember all the building blocks, right? We have 6 classes of the building blocks: constant functions, power functions, exponential functions, log functions, all the trig functions, all the inverse trig functions. Okay, and then you just remember we're trying to differentiate all the building blocks. Okay, three more formulas. Okay. To differentiate the inverse sine of x, the derivative of inverse sine of x is equal to 1 over square root of 1 minus x squared. It's actually the same thing as the derivative of arc sine. I told you these two notations are the same thing. Okay. And likewise, the derivative of inverse cos of x is equal to negative 1 over square root of 1 minus x squared. The derivative of inverse tan of x is equal to 1 over 1 plus x squared. Okay. As I mentioned earlier, in the future, at the right time, it's not quite possible for now. So very shortly, I can show you why the first formula is true, why the derivative of a constant is equal to 0. I think the second one, how to differentiate the power functions, I partially told you true. I partially told you why the formula is true. We have seen why the formula is true when n value is 3. We differentiated x to the power of 3 last class using the definition, right? I just said I could tell you partially why the formula is true. Actually, I told you why the two special cases are true using definition, right? Again, for all other formulas, at the right time, I'm going to tell you why all other formulas are true. So probably not all other formulas. Probably I cannot tell you why the derivative of sine of x is equal to cos. That's the only one you need to read textbook if you really want to know why. Okay. Other than that, I can show you why all other formulas are true. Okay, at the right time. At this point, you just memorize the formulas. Okay. I'm going to move on to the next slide. Now I want you to take a picture, probably take a picture of this slide, so you have something to follow. That's kind of your formula sheet. Probably you have copied on the the formulas on your notes already. Okay. Can I move on now? Now take a picture, please, if you haven't. If you didn't copy the formulas on your notes. Okay. Now I'm going to move on. Okay. The first formula, I'm going to tell you why right now. Okay. We do not use c, so can I use a particular constant of 5? No, for instance. If the function is equal to the constant of 5, now I'm going to show you how to get the derivative of the constant. Okay, find the constant, find the derivative of the function as a function. Okay. Okay, now the solution. The only way we can use is to use the definition of the derivative. Okay. Now let's recall the definition of the derivative is the following. We did many questions last time, I think, right? It's defined as the limit of a difference quotient as h goes to 0. The denominator is h. The numerator is f of x plus h, right? Minus f of x. That's the basic formula I told you to memorize last time. So that's actually how we define the derivative of a function as a function. Okay. It's a constant function, which means the value of the function at any number is equal to 5. Anybody want to tell me the value of the function at x plus h? Now look at the mouse cursor. Look at the mouse cursor, please. So anybody want to tell me the value of the function at x plus h? I know people tend to be more confused for simple things, but so this one is very simple. So don't overthink anything. Okay. What's the value of the function at x plus h? The function is a constant function. Yeah, it's 5, which means the value of the function at any number is equal to 5, right? In particular, the value of the function at x plus h is 5. The value of the function at x is 5. Do you see the numerator is actually 0? And then when you take the limit, you take the limit of the constant function of 0. So the limit is equal to 0. Right. Now you look at two sides of the equation. Look at two sides of the equation. It means the derivative of 5 is equal to 0. Right. I believe you can see the argument is true for any constant. For the constant 5, for the constant 10, for any constant. So that's why the first formula is true. Okay. For all these formulas, it's kind of the matter of how to memorize all the basic formulas. But I'm going to make some more comments on power rule. Okay. Because power function is a very big class of functions. Okay. It consists of many radical functions and so on. Okay. I will make more comments on this by doing some more questions. Okay. Again, on this slide, I'm going to make some comments on the famous power rule. Okay. Again, so this one is called the power rule. It's for the derivatives of all the power functions. Okay. Okay. So how about we start from the comment I want to make is that n is not necessarily an integer or a positive integer. Actually, n can be any real number. N can be any real number as long as n is not equal to 0. There's a restriction. The only restriction on n is not equal to 0. N can be any real number. Okay. N can be 2, can be -5, can be 0.3, can be 1/2. As long as n is not equal to 0, n can be any fraction, can be any real number. Can be any real number. Okay. Using that, I'm going to. So how about we just try a few questions? Okay. Now, for example, if I want you to differentiate, so now let's say the derivative of 1 over x. Now let's compute the derivative of 1 over x using the power rule. I told you that's actually a special case of the power rule. We have seen why this formula is true using the definition of the derivatives, right? But now we are going to use the power rule to verify the formula is indeed true. Okay. The derivative of 1 over x. We have a formula for handling the derivative of any power function. 1 over x, we mentioned before, is essentially a power function, right? Before using the power rule, we have to convert the function to the form of a power function before we can use the power rule. Okay. Anybody can recall, write in the chat, how can we convert this function 1 over x to the form of the power function? It's x to the power of -1, right? It's x to the power of -1. So we convert 1 over x to the form of the power function. Okay. The inside part 1 over x is essentially x to the power of -1. Okay. We take the derivative of that. Now we can use the power rule. This is a particular case with n value is equal to -1. We're going to apply the power rule for n value of -1. Now you look at the formula, okay? The derivative of x to the power of n is equal to, I'm going to say n, by n I mean in this particular case n value is -1, okay? The derivative of x to the power of n is equal to n times x to the power of n minus 1 at this point, at this location. Exponent, I mean, at exponent is going to be n minus 1. So -1 minus 1. So at this location, you're going to have -2. Is that right? Again, to differentiate a function like this, the first thing you do is to convert the function to the form of a power function. 1 over x is x to the power of -1. You only look at the inside part, okay? The part inside the brackets. After converting the function to the form of a power function, okay, and then you can use the power rule. Using the power rule, the derivative of x to the power of n is equal to n times x to the power of n minus 1. In this particular case, n value is -1. n minus 1 is -2, of course, right? In most cases, when I want you to differentiate a function, you do not need to simplify, okay? But in order to verify this formula is the power rule is consistent with the formula I told you to memorize before. I mean, the derivative of 1 over x is actually the same thing as -1 over x squared. I'm going to use the formula. I'm going to convert this form to some other form. So this one is actually the same thing as -1 over x squared, right? I told you this one is a particular case of the power rule. We have seen why this formula is true using the definition of the derivatives, right? I just showed you why this formula is true using the power rule. Actually, we have seen why this formula is true using the definition. Okay. Any questions? Yeah, probably I'm running too slow. You got it already, I guess. The next one we're going to work on is how to use the power rule to differentiate the function. So now let's say square root of x. Okay. Again, the first thing we do is to rewrite the function to the form of a power function so that we can use the power rule. Okay. Square root of x, we rewrite the function in the form of a power function as x to the power of 1/2. From the assignment, from I think assignment 2. I guess all of you guys have no problems with this. Okay. How to convert a radical function to the form of a power function. You still have to write the prime notation to mean we are taking the derivative of the function. Okay. Now we can use the power rule to differentiate x to the power of 1/2. So this is a particular case when n value is 1/2, right? Now we can use the power rule. The derivative of x to the power of n value is 1/2 is n times x to the power of n minus 1. n minus 1, it means 1/2 minus 1. 1/2 minus 1 in this particular case is negative. It's negative 1/2, right? Okay, to make the form consistent with the form I told you to memorize, I'm going to rewrite the function in the form of 1 over 2 square root of x. Okay. Any questions about this? Actually, I told you to do many questions about how to convert some radical functions to the form of the power functions and so on. Okay, so that's where I'm using it. And probably, if you want, I can recall the basic formulas I wanted you to memorize. Okay. So now let's say to convert a function in the form of now let's say 1 over x to the power of m. To convert this function to the form of a power function, the formula you need to use. I was trying to write m. Okay. The formula you need to use is x to the power of negative m. On the right hand side you have the formula of the power function, right? On the left hand side you have 1 over x to the power of m. Two more formulas. One other formula I wanted you to memorize is nth root of x to the power of m. I think that's the notation I used before. So this one can be converted to the form of a power function as x to the power of m over n. Is that right? And one more. Okay, if you have a radical in the form of 1 over nth root of x to the power of m, the formula you need to use is x to the power of m over n. Sorry, negative m over n. Okay. So just a review about what I told you to memorize before. Okay. I'm going to make more comments on the power rule. Okay. Now more examples. Okay. Now for instance, if I want you to differentiate, to take the derivative of x to the power of 10, use proper notation please. So this one is a particular case when n value is equal to 10, right? The formula you need to use is 10 times x to the power of 10 minus 1, n minus 1. So in this particular case is x to the power of 9. Okay. This one is simple too, right? Now let's try one more. Okay. And now let's try a few more. Okay. Essentially, it's practicing how to convert the functions to the form of power functions. Now let's say if I want you to differentiate 1 over x to the power of 5, the first thing you do is to convert the function to the form of a power function. Okay. The inside the brackets you have x to the power of negative 5, right? You differentiate that. Now the function is in the form of a power function. It's a particular case when n value is negative 5. Okay. The answer you are going to get is n times n value is negative 5, n times x to the power of n minus 1. Negative 5 minus 1 in this particular case is negative 6, right? A little bit more comments. In most cases, you do not have to simplify. I'm trying to say you can leave that form as the final answer. I'm trying to say you do not have to convert the answer to any other forms. Okay. I will show you, so maybe two more, and then I will ask you to try a few questions and write your answer in the chat. Okay. So maybe if I want you to differentiate the function, now let's say square root of x cubed, you have to write the prime notation in here. To me, we are trying to differentiate the function. We are trying to take the derivative of the function. Okay. Now the first thing you do is to convert the function to the form of a power function, so which is x to the power of 3 over 2. Is that right? Using one of the formulas, convert the function to the form of a power function. You take the derivative of that. I told you n can be any real number as long as n is not equal to 0. This is a particular case that n value is 3 over 2. Now we can apply the power rule. Okay. Apply the power rule. You have n. The derivative of x to the power of n is equal to n times x to the power of n minus 1. 3 over 2 minus 1. I think it's 1/2, isn't that right? 3 over 2 minus 1 is 1/2. That's how we use the power rule to differentiate square root of x cubed. Okay. It's kind of weird why people come and go all the time. Probably somebody has internet problem, and I don't know. Okay, one more, and then I will ask you to try a couple. Okay, so maybe the next one we're going to evaluate is 1 over whatever we want. Okay, so now let's say cube root of x squared. We differentiate that function. Okay, to differentiate this one, yeah, the same thing. As long as you know how to convert the radical function to the form of a power function, then you should be okay. Inside the brackets, the conversion is the function can be rewritten in the form of a power function as x to the power of negative 2 over 3, is that right? Using one of the formulas I just reviewed. So this one is a particular case when n value is negative 2 over 3. Okay. The derivative of x to the power of n is equal to n times x to the power of n minus 1. In this particular case, negative 2 over 3 minus 1. I think you have negative 5 over 3. Negative 5 over 3 is negative 2 over 3 minus 1, right? These are probably enough questions for the comments on the power rule. Okay. Again, as long as a function that can be converted to the form of a power function, then we can use the power rule to differentiate the function. So that's the point. Okay. And then you want to review in the first week, I told you how can we build all the functions we need in this course. We can perform some operations to build many functions, right? To build all the elementary functions. Those operations including addition, subtraction, multiplication, division, and probably more importantly, composition. Okay. We mentioned the operations before. Okay. Now we are going to learn how to differentiate. So now let's say the sum of two functions, the difference of two functions, the difference between two functions. Okay, and the product of two functions and the quotient of two functions and so on. Okay. But before that, now let's concentrate on how to differentiate the sum of two functions and the difference between two functions and the scalar multiple of a function. By that I mean this is called scalar multiple of a function. Okay, we can use a number to multiply a function. Now temporarily we concentrate on the first three properties. Okay, by that we mean now look at the first property. Okay, I will show you some particular cases very shortly. The first property, it says a scalar multiple of a function. If we differentiate a scalar multiple of a function, you can leave out the constant, and then you use the constant to multiply the derivative of the function. Okay. The second property says to differentiate the sum of two functions. The sum is the answer to addition. Okay. To differentiate the sum of two functions, the derivative of the sum of two functions is equal to the sum of two derivatives. Okay. And likewise, the difference between the derivative of two functions is equal to the difference between the derivatives of f and g. we concentrate on the first three formulas first. Okay. I will illustrate the meaning of the properties using some particular questions. Probably it's easier if I copy the properties onto the PowerPoint, so I can make some more comments. We don't prove the properties, so but if you really do want to prove so these properties, it's not hard, it's not too hard at all. Okay. If you read textbooks, it's using the definition of the derivative. It's easy to prove all these properties. Okay. Now I'm going to temporarily remove the last property. I'm going to mention to make some comments on the first three properties. Okay. Now, for example, the following is designed to illustrate the first property. So can I label the properties using 1, 2, and 3 so that it's easier for us to communicate. Okay. Now I'm going to make some comments on property number 1. Okay. Now, for instance, if I want you to take the derivative of, now let's say 5 times e to the power of x, if I want you to differentiate that, in this particular case, you treat 5 as c. Okay, you treat e to the power of x as f of x in the first property. Okay, the first property says it's permissible to leave out the constant, of 5, and then you take the derivative of e to the power of x. Now look at your formula sheet. Before the next class, I really hope you can memorize all the basic formulas. Okay, but for today's class, you can look at your phone or the formula sheet, the basic formulas I just told you. So the final answer is 5 times e to the power of x, right? Because the derivative of e to the power of x is e to the power of x. I told you the formula before, right? Again, the question is designed to illustrate how to use formula number 1. Okay. For this type of the questions, as long as after you eliminate all the prime notations, then you are done. I mean, the derivative of a function, the answer is a function. Okay. Okay. Now look at number 2. Now look at formula number 2. Okay, I'm going to use a particular question to illustrate formula number 2 now. Okay. Now, for instance, if I want you to take the derivative of, now let's say sine of x, and then plus, how about we just use two trig functions, and then tan of x. We take the derivative of the sum of the two functions. Now we're going to apply formula number 2. Okay, formula number 2 tells you the derivative of the sum of two functions is equal to the derivative of sine of x, and then plus the derivative of tan of x. So do you see property number 2? It means the derivative of the sum of two functions is equal to the sum of two derivatives, right? The derivative of the sum of two functions is the same thing as the sum of two derivatives. Okay, now look at the basic formula. The derivative of sine is cos of x, right? And the derivative of tan of x is equal to secant of x, the whole thing squared. And by the way, what we are doing right now is the differentiation techniques. We are going to learn many techniques for differentiating many functions. Okay. Okay, represented by again, that question 2 is designed to illustrate property number 2. Okay, now you have seen what's going on. Any questions so far? Actually, as long as you know what's going on with question with property number 2, you just replace addition with subtraction. So question number 3 is actually the same thing. So how about that? I'm going to replace all the additions with subtractions. I will make up one more question. So can I call this question number 3? If I want you to differentiate the difference between these two functions, all we need is to replace the plus signs with minus signs. So you can have the derivatives of sine of x minus tan of x, right? Simple. Actually, many questions are the functions could be more complicated than what I just showed you. So now let me try to make up one other question. So basically, we're going to combine all the first 3 properties to do some questions. Okay. I will make up one other question. Okay. Now, for example, so this time if I give you a function y, and by the way, we can replace f of x with y, so you know that. So that's the standard dependent variable notation. Okay. If the function of y is equal to, so now let's say 2 times sine of x, and then plus 3 times e to the power of x. If the function y is defined as the function of x as that, if I want you to find or evaluate the derivative of y, I'm going to show you how. Okay. We'll do the question in a longer way and a shorter way. We'll do the question using a longer way first, okay? And then I'm going to tell you how to do the question using a shorter way. The derivative of y, in this particular case, we are trying to differentiate the function y, okay? The derivative of y, we copy y as a function of x. By that we mean we are trying to differentiate the function 2 sine of x, and then plus 3 e to the power of x. We are trying to differentiate that, right? The first thing you'll see is addition in here. By that we mean I want you to treat the whole thing as the sum of 2 functions. One function is the 2 underlined functions. I want you to treat the function inside the brackets as the sum of 2 underlined functions. Okay. So we can apply property number 1. By property number 1, I mean property number 2. We apply property number 2. Okay. The derivative of the sum of 2 functions is equal to the sum of two derivatives, right? By that we mean you differentiate 2 sine of x, and then plus the derivative of 3 e to the power of x, right? And then for each of these 2 terms, we can use property number 1. Now look at the property number 1. Property number 1 says you can leave the constant out of the prime notation. By that we mean using property number 1, the first term will become the derivative of 2. The first term will become 2 times the derivative of sine of x. And then the second term, it becomes 3 times the derivative of e to the power of x. At this point, everything is in the basic formula. I mean, the derivative of sine of x and the derivative of e to the power of x are in the basic formula. Okay. For the people who joined the class really late, now you get your phone, so take a picture of this screen. We mentioned the derivatives of all the basic elementary functions. Now take a picture of that screen now. Understand? Okay, now I'm going to move on to the questions, to the question we're doing right now. Okay. According to the basic formulas, the derivative of sine of x is cos of x. So we end up with 2 times cos of x. Okay. And then plus the derivative of e to the power of x is e to the power of x. It's itself. So we have 3 times e to the power of x. Again, after getting rid of all the prime notations, then you are done. That is the final answer. In many cases, you do not need to simplify. Actually, this one is simple enough, so there's no way to simplify further. Okay. Any questions about this? Fortunately, in the future, you really do not have to show that much of work. So this is my long way. I told you this is my long way. Okay. In the future, as long as you know what's going on, you can remove all the middle steps. I'm trying to say you can remove all these steps. So that's kind of the standard notation to remove, right? You can remove all these steps. You can just go from, now look at the mouse cursor, from that step to this step. By that we mean it's permissible to differentiate the function term by term. You can just leave out the constants. Now for instance, to differentiate that function, you just, the derivative of the function is 2 times the derivative of sine, so which is cos, and then plus 3 times the derivative of e to the power of x, so which is e to the power of x. Okay, finally we are ready to do some questions on the handout. I told you to get a copy of your handout. Okay. We'll do 2 more questions before we take a little break. Okay. Now look at question 1. Okay. In the future, for all the questions, you do not use the long way. Okay. You can use the short way. By that we mean, now for instance, to take the derivative of y, you can differentiate the function term by term. For this function, we mean the derivative of y. I'm going to write solution. The derivative of y is actually the same thing as the derivative of x to the power of 100. You do not even have to copy this. And then plus square root of x, and then plus 1 over x, right? And then plus 1. You do need the prime notation if you want to copy the question. Or you could even remove that step by looking at the original function. But here you do need to write y prime to mean we're trying to differentiate y. We're trying to get the derivative of y. Okay. So differentiate the function term by term. By differentiating, we mean taking the derivative. Okay. We take the derivative term by term. Differentiate x to the power of 100. It's a particular case of the power rule, right? n value is 100, you have n times x to the power of n minus 1. 100 minus 1 is 99. Okay. For three other terms, I told you to memorize, right? I told you to memorize the basic formulas. The derivative of square root of x is equal to 1 over 2 square root of x. Is that right? The derivative of 1 over x is negative 1 over x squared. The derivative of the constant of 1 is equal to 0. You do not have to write the 0 term. So that's the final answer. Simple enough. I told you we'll do one more question before we take a little break. Okay. How about we do question 3? Okay. We'll do question 3. This time I'm going to be lazy a little bit, okay? I'm going to write y prime in here, okay? Taking the derivative of y, you write y prime. It means you take the derivative of that function. Differentiate the function term by term. But we do not run too fast. So this time, we have handy formula for x to the power of 100. We have handy formula for the first three terms, square root of x and 1 over x and so on. But before differentiating, we want to convert these two terms to the form of power functions before we can use the power rule. Okay. Still, I'm not differentiating the function yet. I'm just converting the function inside the brackets to some different forms. In particular, for the third last term and the second last term, I want to convert these two terms to the form of power functions before we can use the power rule. Okay. You will know what I mean. Okay, x to the power of 100. I just copy that. We have a handy formula for the derivative of square root of x already. I just copy that. And then we have a handy formula to differentiate 1 over x already. Okay. But this term, now you look at the mouse cursor. So that term, I want to convert this radical function to the form of a power function as x to the power of 4 over 5. Is that right? And then likewise, I want to convert the next term to the form of 2 times, you know where this 2 is coming from, right? 2 times x to the power of negative, I think 3 over 4. I think I got this right. And then you just plus pi. I hope you know what we are doing right now. Why I want to convert, now look at the mouse cursor, these two functions to the form of the power functions. So because only after we convert the function to the form of the power functions, we can apply the power rule. So that makes sense? At this point, we know how to differentiate every term inside the brackets. That's a common mistake. I made a common mistake. So do not forget the prime notation. Okay. And then every term is kind of a power function. I mean, every term you have for each term you have a handy formula to differentiate the term. Okay. The derivative of the first term is 100 times x to the power of 99. We have a handy formula for that, the power rule, right? And then to differentiate term 2, we have a handy formula as well. The derivative of square root of x is 1 over 2 square root of x. Check your formula sheet. I told you to memorize. That's a particular case of the power rule. Okay. And the derivative of 1 over x is negative 1 over x squared. I told you to memorize too, right? Now you see why convert the next term to the form of x to the power of 4 over 5. Now to differentiate the underlined term, I'm differentiating the underlined term. We want to use the power rule. That's a particular case when n value is 4 over 5. The derivative of that term is equal to n is 4 over 5, n times x to the power of n minus 1. 4 over 5 minus 1 is negative 1/5. Is that right? For the underlined term in the new line, the underlined term on the new line is the derivative of underlined term in here. Okay. All right. So one more term. So for that, it's because the derivative of pi is nothing but 3.14 something. It's a constant. The derivative of the constant is 0. We just need to differentiate one more term, the double underlined term. Okay. The double underlined term, you leave out this constant of 2, okay, and then you differentiate x to the power of negative 3 over 4. In many cases, you do not have to simplify. I'm going to write a longer way. It's acceptable as the final answer. You leave this 2 in here. You leave out the 2, okay, and then you differentiate the function, the power function in the box. Okay, so you have 2 times n times n value is negative 3 over 4, right? N times x to the power of n minus 1. In this particular case, negative 3 over 4 minus 1, you have negative 7 over 4. I think I got this right. If you want, it's possible to simplify the coefficient, the number before that function, but it's okay. You do not have to. Okay. I'm trying to say this one can be treated as the final answer. The questions in part 1 are designed for property 1, property 2, and property 3. Okay. The rest of the time we are going to talk about how to deal with the derivative of the product of two functions and the derivative of the quotient of two functions. Actually, these two formulas, they have names. Now look at the mouse cursor. That formula is called the product rule. It's called the product rule. Okay. This formula is called the quotient rule. I'm going to write the name down. Okay. This one is the product rule. This one is the quotient rule. You remember I told you how we built all the functions we need in this course. We can perform multiplication, we can perform division, addition, subtraction, and more importantly, composition, and so on. Right? The product rule is for handling how to differentiate the product of two functions. Likewise, the quotient rule is for differentiating the quotient of two functions. Okay. We'll use a few questions on handout to show you how to use the product rule and quotient rule. Okay, now let's go over question 1. In question 1, we are trying to differentiate x squared times cos of x. In the function, you see you have the product of two functions. Okay, you have the product of two functions. So basically we're trying to differentiate the product of two functions. It's a common mistake to do the following. I'm trying to say, so do not do the following, okay? Do not do the following. It's very wrong. Do not do the following. The derivative of x squared is 2x using the power rule, right? The derivative of cos of x is negative sine of x. So do not do it that way, okay? It's very wrong. I'm trying to say the derivative of the product of two functions is not equal to the derivative of the two functions. It's very wrong to do that way, okay? To do it properly, you have to use the product rule. The product rule is here, okay? You treat x squared as f of x in the formula. You treat cos of x as g of x in the formula. I know these two factors are commutative, okay? But I want to call x squared the first factor. I want to call cos of x the second factor, okay? The product rule says to differentiate the product of two functions, I want you to copy the formula, okay? By copying the formula, I mean you replace f and g with two particular functions you identified as the two factors, okay? By that we mean your f of x is x squared, right? Your g of x is cos of x. Now we follow the formula. We call x squared the first factor. We call cos of x the second factor, okay? The product rule tells you the derivative of the product of two functions is equal to the derivative of the first factor times the second factor, and then plus the first factor x squared times the derivative of the second factor. That's what I meant by copying the formula, okay? Copy the formula so you have something to follow, okay? And then each of the derivatives are in the basic formulas, right? The derivative of x squared is equal to 2x according to the power rule, okay? And then times cos of x, and then x squared times the derivative of cos of x is negative sine of x. You could rewrite the function in some other form. By that we mean it's okay to put the negative signs before the two functions. But in many cases, I told you, you do not have to simplify. You can leave the answer like that. It's fine, okay? So that's a typical simple question designed for the product rule. Again, in the future, if you see you are trying to differentiate the product of two functions, you use the product rule, okay? Use the product rule properly. I meant commonly used wrong formula is the following: the derivative of f of x and then times g of x. So do not use that formula, okay? So do not use that formula. It's not equal to the derivative of f times the derivative of g. So do not use that formula, okay? So this formula is true. It's wrong. Simple enough? Actually, on the screen you have my draft version of your next assignment. You're ready to do question 1, 2, and 3. So later on, I will show you the meaning. Okay. I will make more comments soon. But now let's try to differentiate one of the functions in question 2. Okay. In question 2, you have f of x equals square root of x times cos of x. Okay. I think in question 2a, what I want you to differentiate the function, you use a notation like this to represent the derivative of the function. It means the derivative of the product of two functions. Again, use the notations properly, okay? I'm looking for proper notations. You do need to write the prime notation here, the prime notation here. Okay. Now we are trying to differentiate the product of two functions. The answer is copy the formula first. The derivative of the first factor times the second factor, and then plus first factor times the derivative of the second factor. Simple enough. And then you have handy formulas to differentiate square root of x and cos of x. Now look at the formula sheet. The derivative of square root of x is 1 over 2 square root of x. I told you to memorize. Okay. I told you to memorize. It's because you see the derivative of square root of x over and over again. So it's easier if you just memorize. You do not have to convert to the form of a power function and so on. Okay. The derivative of cos of x is negative sine of x. So simple enough. As long as you know the basic formulas, actually I do not have too many harder questions for the product rules and the quotient rules. Yeah, probably that's the case. It's not possible to give too hard questions for product rules and quotient rules. Now let's look at a question designed for the quotient rule. Okay. As long as you know the formula, I believe it's the questions are easy. Now I'm going to use a question on the handout. Okay. Any question you want. So how about we do question number 5. Again, copy the formula first. In the formula, f of x is the numerator, g of x is the denominator. The only thing I want you to be careful is the minus sign here. Okay. So do not forget, do not use a plus sign. It's actually a common mistake. For the quotient rule, you have a subtraction in here. Okay, now for question 5, I will give you the solution. Can start from here. The derivative of y is equal to, copy the formula first. By copying the formula, I mean you treat g of x as natural log of x, and then you treat f of x to be the whole numerator. Okay. On denominator, the derivative of the function y is equal to g of x, the whole thing squared. G of x, the whole thing squared. It's possible to write the little 2 in here, but so people do use notation like that. But I still prefer to write natural log of x, the whole thing squared. Okay. And then the polynomial on the numerator is f of x, right? You take the derivative of the numerator, so which is the derivative of x to the power of 6, and then plus 2x, and then plus 4, the derivative of f, and then times g of x. Your g of x is natural log of x. Okay. Minus, so do not forget you need to use a subtraction here. Minus f of x, so which is x to the power of 6, and then plus 2x, and then plus 4, and then times the derivative of g of x. The derivative of natural log of x, right? Okay, we're almost ready to get the final answer. Actually, in the basic formula, can I add one more formula? You can treat the next one as a special case of the power rule. But I want to add one more in here. Anybody want to tell me the derivative of x? The derivative of x, you treat x as a function, the linear function. You can see that as a power rule, but or it's easy to use the definition to check. The derivative of x is equal to 1. The derivative of x is equal to the constant of 1. Add that one to the basic formulas. Okay. So maybe you could put that under the power rule. It's easy to verify using the definition of the derivatives. Okay, now at this point we are ready to differentiate all the functions in the basic formula, right? So the denominator is natural log of x, the whole thing squared. Now it's easy to differentiate the polynomial. That's a polynomial of degree 6. The highest power here is 6. We say it's a polynomial of degree 6. Okay. Differentiate that term by term using the power rule. I think you have 6x to the power 5. And then the derivative of 2x. I told you the derivative of x is equal to 1. The derivative of 2x is equal to 2, right? And then the constant 4, the derivative of the constant 4 is equal to 0. Inside the brackets, you have the derivative of the polynomial. Okay. And then natural log of x, you just copy that, minus copy x to the power of 6, and then plus 2x, and then plus 4. The derivative of natural log of x is equal to 1 minus x. Okay. The derivatives can get a little ugly. You see the answer is a little ugly already. Okay. But differentiation, the derivatives are super useful in many senses, so engineering and so on. So they think it's very useful. Actually, we're on chapter 3, so later on we'll go back to chapter 2, of course. Okay. In chapter 4, I'm trying to say, in chapter 4 we are going to learn many applications of differentiation. So they think has many applications. Okay, so that's one of the questions, showing you how to use the quotient rule. Yeah, that's question number 5. Okay. So temporarily, so do not worry about the 4, 5, 6, and 7, and 8 yet. Okay. These questions are designed for the chain rule. Chain rule is designed for differentiating the composite of two functions. For the assignment, I'm going to remove these questions and adding some more questions for the product rule and the quotient rule. Okay. So how about I think we did 2a. Now let's look at 2b. Okay. For question 2b, it's possible. I told you it's permissible to use the answer to question 2a. Okay. Now let me copy 2b to the to the PowerPoint. I think the answer to 2a is here, right? Now I'm going to work on 2b. Okay, I will show you how to do 2b. 2b, you see the big picture of the function is the quotient of two functions, but on the numerator you have the product of two functions. I hope it makes sense. This question is designed for the purpose of quotient rule followed by the product rule. When you see the quotient of two functions, you have to use the quotient rule. Okay. When you see the product of two functions, you have to use the product rule. I will show you what I mean. Okay. I hope I have enough space. Let me try to do it this way. A little bit to the left, and then I will divide this part into two parts. The derivative of the function, again, you treat the whole picture as the quotient of two functions. We have to apply the quotient rule first, right? We do quotient rule first. The denominator squared, tan of x, the whole thing squared, right? And then on the numerator you have the derivative of the numerator, so we just copy the formula first. The derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. So that's the quotient rule, right? I think you'll have quotient rule on your notes. Now you check your notes, or you look at the formula here. Okay. I did nothing but using the quotient rule. Okay. Now I told you it's permissible to use the answer to A. By that I mean, now look at the cursor, okay? For the derivative of square root of x, so times cos of x, you did that in 2a. You can just borrow the answer from here. I'm going to remove the vertical line. Okay. I think the answer is going to be a little ugly, a little bit long. I'm going to copy the answer to 2a. I mean the derivative of that factor from 2a. You have, it's a little ugly now. Okay, 1 over 2 square root of x, and then times cos of x, and then plus square root of x, right? And then times negative where is it? Sine of x. Everything is in brackets, and then times tan of x, right? So be careful here, the brackets are essential. Without brackets, it would mean something different. The denominator is tan of x, the whole thing squared, you copy that, and then minus square root of x, and then times cos of x. The derivative of tan of x, now you look at the formula sheet, you have secant of x, the whole thing squared. After getting rid of all the prime notations, after evaluating all the derivatives, and then you are done.